Good morning, everyone. We're going to continue this morning in chapter 10, and I think we're going to finish up chapter 10, and then we'll move into chapter 11 on Friday. So we were on this slide last time talking about the distribution of speeds within a sample of a gaseous compound or a gas. So if we have a gas, imagine you have helium in a gas cylinder. So we have a bunch of helium atoms. And so the helium atoms, or whatever the atom is, are going to have a range of molecular speeds. So we're going to have some very slow molecules or some very slow atoms, some very fast moving atoms. And then on average, our average is a little bit off of the peak. The peak would be the most probable velocity. The average is a little bit skewed off that point because this isn't a perfect parabola. So we have more particles on the faster side than we do on the slower side. So we have a distribution that's skewed onto the faster side. So our average velocity a little bit higher than that most probable point. And then we also identified a point called the root mean squared velocity. That's just the velocity that is related to the average kinetic energy of the particles, where the kinetic energy just comes from 1/2 mv squared for average kinetic energy. And so kinetic energy, we were talking previously last time that temperature is related to kinetic energy. That as we increase temperature, we increase that average kinetic energy. Therefore, we're going to average out to having higher velocities, but on average. And so if we go from 0 degrees C in the blue curve to in red, the 100 degrees C, that we have on average higher velocities. And so we still have, even at 100 degrees C, still some particles are slow, some are still even faster, but on average, we're just a tick up. So our most probable is a little bit higher, our average is a little bit higher, and our root mean square would be a little bit higher than at 0 degrees C for that gas. And so we can calculate some of these parameters. And so there's a couple of equations that will relate the calculation of root mean square velocity most probable. There's even an equation that we won't get into for the average, but the most probable velocity is equal to the square root of 2 pi RT divided by the molar mass. And then the root mean square velocity is 3 pi RT divided by molar mass in that square root. And so there are some fundamental equations that relate the calculation of the root mean square velocity, which is a little bit higher than our most probable velocity. So if you notice, the only difference here is the number 2 versus 3 in the equation. And so that's where those are coming from. And so the one of the keys, though, too, is that you can see from this equation that as you lower the molar mass of a gaseous compound, then you're going to increase the velocity of the particle. So if we're comparing the velocity of, say, H2 on average with oxygen, the difference here is that the molar mass of oxygen is 32 grams per mole, and then hydrogen is 2.016 grams per mole. And so the hydrogen particle is lighter than the oxygen particle, and so hydrogen on average is going to have a faster set of velocities. So the most probable, the average, and then the root mean square velocity, all a little bit higher for H2 than they are for O2. So the heavier the particle, the slower it is on average. The lighter the particle, the faster it is on average. As I was looking at these equations, I think it's just 3RT. I don't think there's actually a pi symbol. So go ahead, cross the pi out for now. So I think I mistakenly put the pi symbol. There's a pi for the average that we don't have on the slide. It's like 8 pi divided by 3 RT or something like that. So it's just 3 RT and then 2 RT. So forget the pi symbol there. Okay, so with that, we have some fundamental equations that relate the calculation of these velocities. So one of the questions might be, how do we actually get a velocity out? And the usual unit we would think is meters per second. This kind of then takes us back to the units of R that we were talking about previously when we derived the 0.08206 number. If you remember, I mentioned there was a number that was 8.314, and a couple of the units were either joules per mole Kelvin or Pascal cubic meter per mole Kelvin. And I said those units may seem strange to you right now and that we would come back to them. Well, we're going to come back to them now because we want to get a velocity out in an SI unit, and that's going to require that our R value that we use here, this is the gas constant R, we want to use the SI units for R. So if we want to get an SI unit out for velocity, we're going to need to plug R in SI units. In atmosphere, the liter atmosphere per mole Kelvin version of R that we use a lot, that's not an SI unit. So we're going to need to shift our use of R here. One thing and so that takes us back to the derivation of the ideal gas constant R. So let's look back at how we derived R. If you recall, we were using the idea that we had a mole of an ideal gas contained a volume of 22.414 liters at STP, and again, at 0 degrees C and 1 atm. And 1 atm is 101.325 Pascal. And so previously for the ATM value, we were just plugging in 1 atm times that volume, and then dividing by the mole at 273.15 Kelvin. So previously we were plugging in 1 atm here, so we're just simply changing that to Pascal for the derivation of R and SI units. So we're just plugging in standard pressure, but in Pascal, and then times liters. We're going to convert liters to cubic meters, because cubic meters is the actual SI unit of length. To get to meter, we have to convert liters into cubic meters. And so this is just either a straight conversion, or if you recall, we could have converted a liter to milliliters, a milliliter to cubic centimeters to cubic meters, but it boils down to 0.001 cubic meters in 1 liter. So we're just using that as a conversion factor to get over to the unit of cubic meters. And so then we do the math here. If we take 101.325 times 22.414 times 0.01, and then divide by 0 degrees C in Kelvin, then we get 8.314, where the units now are Pascal cubic meter per mole Kelvin. So it's like liter atmosphere per mole Kelvin, but converted to Pascal and cubic meter. Well, if we think about what the units of Pascal are, if you remember, a unit of pressure is a force exerted onto a square area. And if you think of how the units of force, now this, you probably don't have to derive this for like your test or anything, but to remember what the units of a Pascal are from pressure is that a force is a mass times an acceleration, and then its area is a meter squared. So the Pascal unit is equal to a kilogram meter to the -1, second to the -2. You can also write that as kilogram per meter second squared, or just the fundamental SI units behind the Pascal. So if you have an SI unit of pressure, there should be some link to the fundamental SI units like kilograms, meters, seconds. And so that's how we can kind of think that there's some relationship between Pascal, kilograms, meters, and seconds. And so then if we kind of rewrite the Pascal times cubic meter, so if I take the Pascal times cubic meter and multiply by cubic meters here in our unit, then we're going to cancel out and to have square meters. So it'd be kilogram meter squared per second squared is what a Pascal times a cubic meter is equal to. So it's like if I just said, oh, you can convert the number and it's the same as a joule, you might just believe me, and that's fine if you just believe me that you can convert this unit here into a joule, but do you recall that this is 1 joule? And so if you can see the math behind it, you can kind of see how we go from Pascal cubic meters, and in fundamental SI units, those boil down to kilograms meters squared per second squared, which happens to be the joule. And so we can express the ideal gas constant with 2 different units. We can either say it's 8.314 Pascal cubic meter per mole Kelvin, or joules per mole Kelvin. And so, but either way, you can see that behind the joule and the cubic meter, we have some fundamental SI units, in particular, kilograms meters squared per second squared. But now where this kind of relates to then getting a velocity is if I'm going to take the square root of a bunch of units where the gas constant's part of it, you can kind of see this is where I'm going to be getting my meters per second out when I do the math and I plug in and try to solve for the math of a particle to calculate its velocity. So calculate the root mean square velocity of the gas particles in an H2 gas sample at 25 degrees C. Now we would give you this equation. You would never have to have the equation for the VRMS memorized, but this would be the square root of like 3 RT divided by the molar mass. But the key here is like how the units work and then seeing what units everything need to be in order for this to work. So I'm going to take the square root of 3 times, now the gas constant, I want it to be this 8.314. And I'm going to write joules per mole Kelvin And then I'm going to multiply that by 298 Kelvin. Of course, I have to go to Kelvin. Now, when I divide by the mass of H2, I have to think a little bit about how I have joules per mole. So I'm going to use a molar mass of H2 to get rid of the per mole. So I'm going to have something per mole, but I'm going to want it to be kilograms per mole because of how the joule has that kilogram unit. So 1 joule, I can think here is that the 1 joule is really a kilogram meter squared per second squared. So what I might write here is instead of the joule, let me change that to a kilogram meter squared per second squared, because that's just simply what a joule is equal to. And so then that's kind of showing me that I want my molar mass to be in units of kilograms per mole, not grams per mole. And so the grams per mole of H2 would be 2.016 grams per mole is the molar mass. So I'm going to want to write here 0.002016 kilograms per mole. So I'm going to want to take the molar mass and just divide it by 1,000. Okay, and so if I take 3 times 8.314 times 298 and then divide it by 0.002016, I get that number, and I need to take the square root of it. So I take the square root, and I get 1920. So this works out to be 1,920 meters per second. So about 2,000 meters per second is that root mean square velocity for a sample of hydrogen gas at room temperature. Now, one last comment here. Let's see how the units cancel. Kilogram cancels, mole cancels, Kelvin cancels. The only units not canceling are meters squared per second squared. We take the square root of the units, we get meters per second. So that's how we get out SI units here. So I don't know if they'll put this on the test or not in terms of how to calculate a velocity, because it is kind of just like a rote problem. But the key detail, I think, is just thinking about units here. That the key detail is if you have to calculate a velocity for a gas sample, you want to use the SI unit version of R. Of course, temperature has to be in Kelvin. Kelvin's the temperature scale for every problem here in chapter 10. And then we want the molar mass to be in kilograms per mole. And that just is how we're applying the definition of what a joule is equal to, and then using the fundamental SI unit. So we just want to put every unit in that problem into SI units. So we're just looking here and saying with this equation here, just put everything into an SI unit and then get out the SI unit of velocity afterwards. Okay, so then if we were to calculate this for O2, so would O2 sample at the same temperature have a greater or lesser root mean square velocity? Without necessarily plugging in the math and thinking about it, what do you guys think? You could also say, would it be equal? It's not going to be equal. So different mass particles, they have the same energy to distribute. So if an equal energy is given to particles, the heavier particle gets a slower velocity, the lighter particle gets a faster velocity. So H2 should have a higher velocity on average, so higher root mean square velocity, and then O2 therefore has a lower root mean square velocity. So O2 should have a lower. And you could prove that if you wanted to. You can just simply repeat the above calculation and just divide by the molar mass of O2. This number here becomes bigger, so the root mean square velocity comes out to be smaller. And of course, if you increase the temperature, you increase that root mean square velocity. You're increasing the distribution of velocities on average. Now, where these velocities play a role are in a couple properties that we call effusion and diffusion. So let's talk about effusion first. So effusion is where you have a pinhole. So there's a hole in this gas container. So we have a gaseous particle inside our container. And then every time a particle actually hits the pinhole, it can escape the cell. And so this is what we call effusion, is the escape from a pinhole. And so the faster the particles are moving, you can think, well, what property could we change to increase the rate of escape of this gas? If we heat up the sample, the particles are bouncing around the container more often. They're going to have a higher probability of hitting that pinhole and then leaving the cell. So you can think, how often is something going to hit that pinhole? It's going to be related to its root mean square velocity. So the rate of effusion is simply proportional to the root mean squared velocity. So anything that increases that velocity will increase that rate of escape. And so R1's the rate of escape of component 1. So imagine we have two components here. So imagine we have a sample of, let's say, helium and O2. So let's say we have two gases together inside of our container. And so we're going to call helium, let's call this particle 1. Let's call O2 particle 2. And so the rate of escape of the two particles is going to be related to their molar masses, but the inverse of their molar masses. And so because our root mean square velocity is equal to 3 RT over molar mass, the rate of escape of a compound is inversely proportional to the inverse of the square root of its molar mass, just from how that's in the denominator of the calculation of our root mean square velocity. And so the rate of escape of compound 1 is inversely related to its molar mass. The same thing for compound 2. And so without even looking at the equation just yet and worrying about the equation, let's just think about the question, helium versus oxygen. Let's say we have an equal number of particles of each inside of our container. Which one do you think escapes faster from this pinhole? Probably helium, because it's just going to be bouncing around faster. Helium's bouncing around faster, O2 is moving slower, so O2 just doesn't hit that pinhole as often. So the problem with O2 is it's just not bouncing around fast enough to hit that pinhole more often. Helium's crazy, rambunctious, moving around very quickly. It's going to hit that pinhole because it's a lighter particle. And so helium's going to escape with a faster rate. And so if helium here is in our equation is particle 1, so say this is helium, rate of escape of particle 2 is the rate of escape of oxygen. So the rate of escape of helium would be equal to the square of those molar masses, and then times the rate of escape of compound 2. And so or let's actually just leave this as a ratio still, and not solve the rate of escape of the 1. So let's leave it as a ratio. But the rate of escape of helium compared to O2, let's actually change this to helium to put these particle names in here so we're being clear on which rate is which. So the rate of escape of helium versus oxygen is going to be equal to the molar mass of oxygen, which is 32 grams per mole. I'm going to leave this in grams per mole because in this equation here, the two molar mass units are going to cancel out into each other, so I can leave those in grams per mole. Helium's molar mass is 4.003 grams per mole, so I don't need to convert to kilograms per mole here. Or if I did, the ratio would still be the same if I convert both of them to kilograms per mole. So the unit itself is canceling out, and so helium is going to escape with a rate of about 8 times that of oxygen. So helium's rate of escape is equal to 8 times that of the rate of escape of oxygen. It's about 32 divided by 4, the square root of that. 32 over 4 is 8, so it's the square root of that times the rate of escape of oxygen. So in other words, by equation, we can see helium escapes faster, and then by thought analogy, helium escapes faster. So helium's bouncing around the container faster, escapes faster than the slower moving O2, and we can apply that with our equation here. So this is Graham's law of effusion. Again, I don't know if you'll see a math problem with this. Usually the conceptual problem, the very simple problems on our next slide that just relates the relative rate of escape is just proportional to the molar mass of the gas. So a common question that we see are ones like this, like which gas below would escape from a tire. Let's say you have a car tire filled up with different gases, and then there's a small pinhole leak. Which particle is going to effuse faster from the tire? And so this is just going to be related, of course, to the root mean square velocity. So again, the higher the root mean square velocity, the higher the rate of escape from that pinhole, the rate of effusion. And so for comparing our molar masses, 32 grams per mole, 44 grams per mole for CO2, but only 28 grams per mole for N2. And so which of those three do you think escapes the fastest from the tire? Probably the lighter N2. And so they're not going to all escape at the same rate because they each have a different velocity. So the nitrogen is bouncing around a little bit faster than the other particles. So it's going to strike the pinhole more often. So this doesn't even come down to, which particle is more abundant in the tire. It just has to do with simply which gas particle and their relative or their actual molar masses, which one has the lighter mass on average is going to move around faster and escape more quickly from the tire. Now, I like to bring this example up here too, because if you go buy car tires, they almost always try to upsell you on filling your tires with nitrogen. I don't know if any of you guys have ever gone into a tire shop and had to replace a tire, but I've seen as expensive in my own experience, $15 they try to charge me per tire to fill with nitrogen. Then they hand you this pamphlet on how nitrogen is so much better for your tire because it escapes slower from the tire. And I'm like, you're crazy. That doesn't even make any sense. You're better off just putting air in the tire. The only reason why you might fill with nitrogen is to get rid of water vapor, I guess, from the rim so you don't corrode the rim. But filling with N2 versus air doesn't make any difference in terms of your tire. It's just a selling strategy car dealerships will use. So I like to say if you can use chemistry to help you understand a sales transaction and save some money down the road, at least we've done something in this class. But so you may encounter that in your real life someday on somebody trying to upsell you on filling with nitrogen. One other detail would be an actual nitrogen gas cylinder costs like $10. You can fill probably 100 tires with a gas cylinder. So I mean, they're charging you $14 or $15 per tire on a cylinder that's costing, $10 per 100 tires. So they're really ripping you off on that sale anyway. So one good thing came from this class, hopefully. We save you some money. Anyways, let's talk about diffusion. So diffusion is slightly different from effusion. So the difference between effusion and diffusion is like we said earlier, effusion is escape from a pinhole, but diffusion is the rate that a gas travels through a medium. So imagine you have some gas particle that's being released into a container. How long does it take to reach the opposite side of the container? So I like to think of this as the smell of coffee aroma, making it from one room to the next when it's being brewed. You can sort of think that it takes, not instantaneous, but the particles of coffee that you can smell are permeating through air. They're bouncing into air molecules, and they're slowly traveling through a room and spreading. So we call that diffusion. And so then the rate of diffusion is related to, one of the big details would be the actual pressure inside the container or the pressure of the atmosphere. If you're thinking of atmospheric pressure, so the surrounding pressure plays a big role in diffusion because the surrounding pressure is what's in the way. So if we had a vacuum system, if I release a particle in a vacuum container, whatever direction it's traveling, it's going to travel until it encounters something that bumps it off that trajectory, and then maybe very slowly has gravity acting on it. So if I release it in this direction here, it might very slowly be moving downward, but it's going to have a trajectory of motion that's not going to be deflected. But if I release the same particle into a room that has a bunch of air, it's going to hit an air particle, move this way, hit another air particle, move this way. It's going to be deflected as it's traveling through the container. And so if the surrounding pressure is higher, so maybe you were thinking this is the pressure of the surroundings, that as the pressure of the surroundings decreases, the rate of diffusion increases. So if you want a faster rate of diffusion, then what you would want to do is have a lower surrounding pressure. I've never done this experiment, but if you're ever at high elevation where the surrounding atmospheric pressure is lower, high up at altitudes, the rate of diffusion should be faster. So you should probably notice that the smell of cooking or coffee or whatever aroma, or if you spray perfume, that it's going to make it to the other side of the room faster than it would at standard atmospheric pressure. So if you reduce the surrounding pressure, you're having less of a block of those molecules to make their escape through the medium. And so we call that mean free path. How long can a particle travel before it encounters another particle? So you're going to get a longer mean free path when you have a lower surrounding pressure. So you get a higher mean free path at lower surrounding pressures. So if you lower that surrounding pressure, you're going to get a longer mean free path. You can also, to get a longer mean free path, have a higher root mean square velocity. So anything that gives a compound a higher root mean square velocity will let it travel on average faster, so it's going to make its way through the medium faster before it encounters something else. And so, of course, having a lower molar mass and then going to generally, if at constant pressure, if you can go to a higher temperature to give that compound a higher root mean square velocity. will allow it to diffuse more quickly through a medium. So rates of diffusion are related to some of the same things of diffusion. So it's related still to root mean square velocity. So faster diffusion with faster root mean square velocity, but we also see the involvement of the surrounding pressure. We want that to generally be lower in order to have a faster rate of diffusion. There's really not too much in terms of diffusion other than a thought analogy question like this slide here. Not really much math behind the relative rates of diffusion. One thing, if you're trying to make a compound that diffuses faster, you generally want it to be lighter. So you want a lighter particle, just like you would want a lighter particle to escape faster from a pinhole. If you're trying to design a compound that can make its way through a medium quicker, you want it to be lighter. Okay, so let's get into the last topic of chapter 10. That's the difference between, or it's really the point where the ideal gas law breaks down. And then when the ideal gas law breaks down, we call that a real gas. So a real gas versus an ideal gas is, the real gas is where the ideal gas law breaks down. So whenever the ideal gas law fails, and then we have a situation where we call that a real gas. So let's talk about, and kind of go back to the ideal gas law for a minute and then think about why it might fail. And so when we're thinking the ideal gas law, PV is equal to nRT. There's two primary reasons why the ideal gas law breaks down. Let's talk about the volume first. And so the volume that we plug into the ideal gas law is always the container volume. But we should really be plugging in the free space volume. The free space volume is the volume that's not occupied by the matter of the gas. If you recall, one of the postulates of the kinetic molecular theory of gases and one of the ideas of an ideal gas is that the gas occupies a negligible portion of the container. So for most gases, especially when you have a relatively low pressure, the gas is not occupying much of the container. So if you're plugging in the container volume, it's approximately equal to the free space volume, and there's no problem using the ideal gas law. But as pressure increases, then the volume of the actual components of the gas, so the volume of the matter, occupies a non-negligible portion of the container. So if we get to a point where the pressure is so high that the actual particles of the gas itself, the matter inside the gas, like the actual matter occupied by the helium atoms if it's a helium sample, or the oxygen molecules if it's an O2 sample, that the volume occupied by the matter, if we're getting to a point where, say, that's like 10% of the container, then we should be plugging in 90% of the volume of the container as the actual volume of our system. So we can get to a point where you can maybe say, well, why don't we just plug in the free space volume by taking the volume of our container minus the volume occupied by the matter. And so you can kind of fix the ideal gas law and kind of say, well, if you wanted to be really careful, we'll see in the equation that does this in a minute, but if you wanted to fix the ideal gas law, you would say, well, just figure out however much space the matter inside your gas sample occupies and subtract that off of the actual container volume and just plug in the free space volume, and you can fix your ideal gas law. And so if you're thinking of, let's think about calculating pressure off the ideal gas law versus trying to correct the ideal gas law. So if we're plugging in and calculating pressure from nRT divided by V and just using the container volume, and we get a pressure, so that's going to be our ideal gas law pressure, and we can compare that to when we plug in the real pressure, or a better calculation of the pressure by taking nRT and then dividing by Vc minus V matter. That we can see, see the effect that we have on the pressure by fixing the actual volume. What we want to do is take the volume, which was, say, 10 liters, and turn it into a volume that's like 9 liters. And so we're turning this number here into a smaller number than it was previously. So we're going to make our real pressure come out to be higher than what the ideal gas law was predicting. I just want us to see that the pressure that the ideal gas law was predicting was too low. So the error we're making in the situation where the volume of the actual matter starts to occupy a non-negligible portion of the container leads to an error in our ideal gas law and an error that leads to an underprediction. So the ideal gas law prediction is lower than the true or the real gas pressure that we're trying to calculate or approximate with the equation. And so we're getting an error in that particular direction. I want to then compare another situation that can lead to an error in our ideal gas law, which is when gases start to experience attractive forces. And so gas particles can be attracted together because we know if you take any gas sample and lower the temperature, eventually that substance will liquefy. And you'll go from having a pressure to then having a liquid which has a much lower vapor pressure. So you can take a sample of a gas where you have a high pressure, and then if you lower the temperature low enough that you get through the condensation point, all that gas condenses and all of a sudden your pressure's gone. And because you now have a liquid. So you may have a small vapor pressure for the liquid, but nowhere near the high pressure you had for the gas. And so what's happening here is that the particles are experiencing that attraction for each other. And then this can start to happen even before you get to the actual condensation point. So let's say we're talking about a sample of water vapor. So water boils at 100 degrees C. So let's say we have a container that's like 200 degrees C. So a really hot container that had some water in it, but it had vaporized. So we have a container of water vapor at 200 degrees C. If we start getting to 110 degrees C, pretty close to that condensation point, we can start to have some particles sticking together more often than they would at 200 degrees C. So the particles are going to start to become stickier to each other when you get closer to their boiling point. This becomes a low temperature problem. So the attractive force problem is a bigger problem at lower temperatures because we're getting close to that condensation point. And so the problem here is if I'm looking at my ideal gas law and I'm plugging in nRT, if particles are sticking together, it's having an error on the calculation of n. And so n should be the number of free particles and so if some of my particles are stuck together, then they're not free particles anymore. So if I had 10 moles of gas in a container, but 2 of the moles of gas were stuck together as one, then I really only have 9 moles of gas in that container because 2 of the moles are stuck together like a dimer. They're attracted together. And so if I had 10 particles, I really only have 9 in reality when they're sticking together. If they're sticking together even more, I only have 8 particles, or I have a fewer number of particles as they're becoming sticky with each other and they're attracted together. And so if I'm calculating my pressure here for my ideal gas law, and I'm just simply plugging in the calculated number of moles in my sample, divide by the volume, and then I can compare that with my real approximation where I then say that this is the actual number of free particles, which is going to be lower. So if I find a way to fix n here, where this number here has to be, let's call it n free particles, that has to be lower than the moles from my ideal gas law. Let's call this n ideal gas law. So you have 10 moles, but if some of them are sticking together, the number of real particles that are free is lower than what the actual calculation of n from ideal gas law was. And so that leads my real pressure to now be the other direction. It leads my pressure real to lower compared to the ideal gas law pressure. So this leads my true pressure to be lower than my ideal gas law pressure. It's a lot of energy for me just to try to show that the high pressure problem leads to an underprediction of the pressure, but then the stickiness problem, the attractive force problem, leads to an underprediction. So these two errors lead to different errors in the ideal gas law in different directions. So they have different directionality in terms of the errors that they introduce that we're trying to correct for or understand for real gases. And so we have 2 problems here. We have a high pressure problem. So we have a high pressure problem that has an error on the calculation of the volume that we're plugging into our ideal gas law. We should plug in the free space volume, not the container volume. And then we also have a sticky problem. We have a attractive force problem that's going to be more apparent at lower temperatures. So as we go to lower temperatures, particles are going to be more attracted together. They're going to have a greater error using the ideal gas law at low temperatures. So we have a high pressure problem and a low temperature problem for 2 different reasons that lead to 2 different errors that could arise. Now, if you had a high pressure but low temperature problem, you have both errors that could, in some ways, maybe cancel each other out. But the key scenario would be if you're at a relatively high pressure, if you're at a really high pressure, but the temperature is not very close to the boiling point, you're at the high pressure problem. If you're at a low temperature, but at a relatively low pressure, so if you have a low pressure, but a low temperature, then you have the low temperature problem. So you have a low temperature problem and a high pressure problem that lead to errors in different directions in the ideal gas law. Now this we can see with a graph like this. This is showing us some different directionality of our errors. We get at low pressure one error and high pressure a different error. So the errors we get in our ideal gas law at low pressures are mainly due to attractive force errors, and then at high pressures we have the volume of the container errors dominating. So two different types of errors that lead to two different types of directionality errors using our ideal gas law. Now there's an equation that we're not going to use this mathematically. That's one of the problems that we actually don't even bother kind of showing you the math behind this, but I just wanted us to see the explanation between the this and the that, between the plus versus the minus. Because what we're trying to correct for here is we're trying to correct our ideal gas law, or PV is equal to nRT, and we're trying to correct the free space problem. And the V minus NB, I think, makes a lot of sense, because what we're doing here is we're trying to calculate V minus NB. This is our free space volume. And the NB is the volume occupied by the actual matter. So we're trying to correct for our free space problem with this equation here by taking our container volume. So V minus NB, the V is our container volume. And then B is a volume occupied by a substance. So the B constant here is related to molecular size or particle size. So as a particle becomes bigger, as you go from like a helium atom to a water molecule, or if you go from neon to argon, you're going to a bigger particle. It's going to occupy more space. So as you go from like neon to argon, notice that the B value goes up. If you compare the values for like something like helium to something like water, so water's way down here, water's higher because it's a bigger particle. Helium's weird in some ways. It's actually higher. I think it's actually an error in our book, to be honest with you. It's always been higher than I think it should be. But if you compare, and maybe don't worry so much about helium, but if you look at the neon to argon to krypton trend, it's increasing because you're going to a larger noble gas. I never had a good explanation why helium is smaller other than it's just some sort of an error for helium. But then if you look at a couple other particles, like if you compare water to CH4, like you're going from this to then adding in that for CH4. So you're going from bent to then having two extra atoms to go to tetrahedral. So CH4 is bigger and has a bigger B value. If you replace the hydrogen with chlorine to go to CCl4, chlorine's a lot bigger than hydrogen. Notice that the B value for CCl4 is a lot higher. So B is just looking at the actual size of a particle within the gas. If it increases in volume or size, it's going to increase that B value. So the particles of a larger gas are going to take up more space in the container. So if you have a mole of neon, it doesn't take up as much space as, like, say, a mole of CCl4. So a mole of CCl4, because it's a bigger particle, takes up more of the container volume. And so N is the moles of your gas times B, so liters times moles gives you liters. I'm not so worried about the math here as I am just about seeing how B is related to the actual size of a particle. We can, in some ways, predict it just by looking at things like how neon, let's not worry about helium, but neon should be smaller than argon, should be smaller than krypton, and that's the same trend as their B values, just in terms of the size of the atoms and then the size of the B value. And then let's look over here at the A value. So the A value is trying to correct for the stickiness problem. So A is trying to fix the pressure of the gas due to the stickiness problem. So this is from intermolecular forces. Our A value here is directly proportional to intermolecular force strengths. So the stickier the substance is with itself, then the bigger correction we need to make. And so then if we're comparing these values here for, say, our noble gases, which aren't very sticky. They're not very attracted to each other compared to, say, molecules like water. Look at how water has a much higher A value than something like helium or neon, because water is polar, has built-in charges, it has a stronger attractive force. If we then compare what's a good comparison? Like if we go to like CO2, which is non-polar, notice that being nonpolar dropped its A value because it is a weaker force of attraction. We're going to talk about intermolecular forces a lot in chapter 11. So the whole existence of liquids are described by their relative intermolecular forces. So substances that have stronger intermolecular forces are going to be more likely to be solids or liquids at room temperature compared to compounds that have weaker intermolecular forces, which are more likely to be gases at room temperature. And so we're going to get into a lot of discussion of what it means to have stronger intermolecular forces in chapter 11. So we're going to talk almost exclusively about these IMFs in chapter 11. So I think the reason why we see a lot of trends that we see in this table will make a little bit more sense as we get into chapter 11. So real gases become more sticky. The A value becomes higher when you have stronger intermolecular forces. We're going to see that you have stronger intermolecular forces in polar compounds, especially when they have H atoms linked up to certain atoms that are really small. So we have hydrogen directly attached to things like oxygen and fluorine or nitrogen. That's going to be really good for creating a strong intermolecular force of attraction that we'll be describing into chapter 11. So that's kind of it for real gases, just kind of seeing A is correcting for the intermolecular force problem, B is correcting for the free space problem of the container, that the B value is a bigger corrective value at higher pressures because we have more particles of gas occupying the container. So as N goes up, so as there's more and more gas in your container, that's going to be a bigger corrective value. And then when the A value actually will change with temperature. As if you look at the A value for a substance, as you get closer to its boiling point or its condensation point, that A value is going to change and become stickier and higher. So A itself is going to become more important or a larger value as you get closer to a substance's condensation point. But it's also then at the same temperature as each other, the A values are proportional to strengths of intermolecular forces. Okay, so let's look at a couple of review problems out of chapter 10, and then we'll wrap up for today after these couple of review problems. And if you want to find these review problems, I added them to the end of the lecture slide page yesterday. So there's, I think, just 4 problems here to look at a couple of review topics from chapter 10. And then, like I said, for Friday, we'll be moving into chapter 11. To look ahead to chapter 11, then afterwards into chapter 12, we're going to spend probably 2 lectures or so in chapter 11, so that'll take us into next Monday. Next week, we don't have lecture on Wednesday, so next week's final day of class is Tuesday. If you didn't see my announcement yesterday, make sure to double check the announcement on recitations for next week. You can actually email your activities next week if you're going to be out of town, or if you'd just rather email it in. You can also attend the very last recitation, which is not scheduled for attendance. That is after we get back from Thanksgiving, that last Tuesday that we have class for recitations. You can attend that day for making up any missed recitation credit throughout the year, just for one possible missed recitation credit. Otherwise, you don't have to go to that last session the Tuesday after Thanksgiving. And then our lecture schedule, in case you don't know this, after Thanksgiving, we're here Monday and Wednesday, then that's it. Then the Thursday after Thanksgiving's reading day, then finals start Friday, and then our final is Monday of finals week, so Monday, December 9th. So just to kind of, another way of saying we have 1, 2, 3, 4, just 4 lectures to go after today. And we'll be spending, like I said, about 2 of them on chapter 11. We'll spend about a lecture on chapter 12, and then we'll get hopefully almost an entire lecture for review, and we'll set up an extra study session sometime, either Thursday or maybe Saturday or Sunday before the final, to do like a Zoom study session. Okay, so with that, let's look at a couple problems here out of chapter 10. Which has the greatest density? So we have 4 choices here. Now, if I see this problem on a test, now I would have to double check. I'm not entirely sure they give you the equation for density. I think they do, and I'm going to write it here, and I can also show how we can get this. It's the pressure times the molar mass divided by RT is density from that we can get from the ideal gas law. Now, if this is not a given equation, I'm pretty sure it is, If this equation isn't given, then we'd have to just simply come back to PV is equal to nRT, and then realize that that moles is just mass over molar mass. And then M over V is density, so I might write pressure times molar mass is equal to M over V RT, just dividing both sides by volume, multiplying both sides by molar mass. And then if I divide both sides by RT, I then have my density is equal to pressure times molar mass over RT. So I think I can get to this equation relatively easily if I had to, just from the idea of ideal gas, just from the idea of what molar mass and mass give us relative to moles, and then just thinking about what density is mass over volume and rearranging. Okay, so for the gases here, we have 5 atm of different gases, but at different temperatures. And so the pressures are the same for each of them, so there's no change in pressure. And so if I have a higher molar mass, I'm going to get a greater density. So a substance with a greater molar mass at the same temperature, same pressure, will have a higher density. So I want a higher molar mass, so it'd be better to have C3H8 than helium. But then do I want the temperature to be higher or lower? Well, if I go to a lower temperature, if I divide by a smaller number, I get a greater density. So I want the lower temperature. And we could mathematically work all these out if we wanted to, because you could go through for each of these. You can calculate the density of each. But I don't think we have to. I don't think we have to go through and calculate the density for each. But the key would be we want the higher molar mass, the substance with the higher molar mass, we want the lower temperature of the two possible temperatures. Now, this I think requires some bit of explanation, because when you see this at first, I think a very common error on a problem like this is just to think, well, at higher temperatures, you get higher pressure. Is to think, well, if I have 298 Kelvin versus 348 Kelvin, the 348 has to have a greater density because that has to be higher pressure, right? It's not a higher pressure, it's the same pressure. So the same pressure, we have 5 atm at both pressures. So think of it this way. If I have a sample of a gas that's 5 atm at 298 Kelvin, so I have my C3H8 at that temperature and pressure. If I want to get that to 348 Kelvin, if I just increase the temperature to 348, the pressure would go up. So how do I get the pressure to not go up? I got to let some of the C3H out. So I have to remove some of the C3H8 from the container. What happens when I do that? The container volume is a constant. I'm letting some of the gas out. The density is lowering. So I get a lower density. I have to let some of the gas out to get to the 348 Kelvin. So this problem to me is a very strange problem. It helps me think about a couple of relationships. That if I increase the temperature, I increase the pressure. But if I can't increase the pressure because it's a constant, I have to leak out some gas. I have to lose some gas, which leads to that lower density. And of course, I can just plug in the math and work it out if I had to. Okay, so that's this question here. This question here, 2 liters at a constant pressure, such as in a container at constant pressure at 25 degrees C is cooled to minus 25 degrees C. What's the volume of the gas sample? Okay, so we probably remember that volume is directly proportional to temperature. If you increase the volume, if you increase the temperature of a gas that can expand, it's going to expand to a greater volume. And of course, this assumes, constant pressure and amount of gas, airtight container, and then constant pressure. Well, and then we had derived this equation here too, where we can have V over T is equal to a constant. So if you change V over T or V1 over T1, the V2 over T2 has to equal the same constant, so therefore they equal each other. So we can have an equation that looks like this, V1 over T1 equals V2 over T2. Now, of course, the key error here would be the negative temperature. So if you're solving for the V2 here, so if we want V2 to be equal to V1 over T1 times T2, from just rearranging this equation here, that we can't plug in the negative temperature, of course. So like if we're thinking V1 over T1 times T2 and just V1 over 25 times negative 25, that this, of course, is not going to be negative 2 liters. And I don't think anybody would think that it's negative 2 liters. But if you don't convert to Kelvin, you may think the answer was negative 2 liters. Of course, you can't flip to negative volume. Because of that, that's why we have to transition or use temperatures in Kelvin. So we have 298 Kelvin here for our T1. So T1's 298 Kelvin, and our T2 is minus 25 degrees C, which is 273 minus 25, so that's 248 Kelvin. And then cooling should lead to a smaller volume as well, so we should take our V1, just 2 liters, divide by 298, and then times 248, I get 1.66 liters. So the main reminder here is just make sure in chapter 10 that you're sending your units into Kelvin. As we then think back, like if we go back to, and we'll see some review problems later in the class, but if you go back to chapter 5, when we were doing calorimetry problems, we had a lot of delta T's. For delta T's, we didn't have to really convert so often. So it's kind of interesting to have a chapter in 5 where, remember where we would have, the delta T from 25 to 27.2, so the delta T was like 2.2 degrees C, and how that was equal to 2.2 Kelvin, and we weren't worrying then about converting to Kelvin, or if we did, we said you gotta convert the 25 and the 27.2 to Kelvin, then take the delta and see it's 2.2 Kelvin. So we had a chapter where we could almost ignore Kelvin. Now we have a chapter where we can't ignore Kelvin. We have to make sure in chapter 10 to make those temperature conversions into the Kelvin scale. Okay. So let's say we have a cylinder with movable piston that can expand against the atmosphere. So the initial pressure, volume, and absolute temperature are P1, V1, and T1. What is the new temperature of the system when the pressure is increased to 3 times its original pressure? So the P2 would be equal to 3 times the original pressure, that was P1, so that's P1 times 3. And then the volume is decreased to 1/2 the original volume. Okay, and so that's my new pressure and volume, and then T2 is what I want to know. That's my unknown. And the relationship between these values is that P1, V1, think about the proportionality to nRT. N's a constant, R is a constant, so I'm going to put T over here. So N and R aren't changing. So we have an airtight container. So we have a P1, V1 over T1 set of conditions that's proportional to N over R. Well, the P2, V2 over T2 have to be proportional to the same NR. So N and R have to be equal to each other. And so that makes P1, V1 over T1 equal to P2, V2 over T2. So I should be able to write that P1, V1 over T1 is equal to P2, V2 over T2. So I just have to solve this expression for T2. And so if I solve the expression for T2, let me put T2 over here, multiply by both sides to get it over to here. And then we divide both sides by P1, V1. And then multiply both sides by T1. And so what I should be plugging in here would be plug in 3P1 for P2. So just plug in what this is equal to here. Plug in times V2, 1/2 times V1. Divide by P1, V1, just from my equation, times T1. So I'm just plugging into this equation here. My P1, my V1 cancels. And so this boils down to 3/2 times T1 is what my T2 is equal to. It's a very extraneous problem, but not the most uncommon example either, because it just sends us through the relationship of P2 and V2 to their original values that we just plug into our expression and then just do the algebra and simplify this down to 3/2 times T1. So 1.5 times T1. Now, the molar mass of a gas, it has a density in temperature and pressure. This just boils back to that equation, G is equal to pressure times molar mass over RT. What I want to do is just convert my pressure to ATM. I want to convert, and I'm solving for molar mass. If I want to solve for molar mass, that would be equal to density times RT divided by pressure. Kind of running out of time. But the idea here would be just convert pressure to ATM, plug in your gas constant, plug in the temperature in Kelvin, and then work out what the density is equal to. I could throw this problem into a packet later to show the math, but we're just plugging into this equation here, and we'll wrap up here for today. All right, guys, I'll see you back here on Friday. Have a great day.